Okay, thank you. Now, very good morning to all. Okay, so in yesterday class, what we have been seeing is that memory management. Can you stop the disturbance? So yesterday we have been seeing about memory management. So some of the techniques of memory management schemes we have been seeing. So just let us review about what we have been seeing in the last class. That is, first of all, we have been defined about what is memory. Memory is a large area of words or bytes, each with its having its own address. The CPU will going to be fetching the instructions from the memory according to the value of program counter. And after that, what we have been seeing is that address binding. So we are talking about address binding concept. So in address binding, first of all, we must know the difference between absolute address and or may call it as physical address. And second one is relocatable address. We have been seeing, and after that we have been seeing that what is compile time address, what is load time address, and execution time address. At the time of translation of source program into machine language, whatever the addresses you are going to be getting, these all addresses are going to be called it as compile time address. And while loading this particular program into main memory, whatever the addresses we have been got, that is going to be called it as load time. At the time of execution, your program may not be complete your execution in a one single memory location. The addresses may be changed at the time of execution. So at the time of execution, whatever the addresses you are going to be getting, that is execution time addresses. And followed by, we have been seen about the concepts of static loading and static linking. Okay, if the loading and linking activities has been done at the time of compilation itself, that is called it as static loading and static linking. In case if the loading and linking activities are postponed until their execution, then it is going to be called as dynamic loading and dynamic linking. And after that, what we have been seeing is that for relay structure by means of a problem example. Okay, how to run a two-pass assembler. Okay, so two-pass assembler. Why? Because pass one, pass two, both softwares are not going to be required at the same time. So after completion of pass one, we are moving into pass two. Okay, so a overlay driver is a small program which is responsible for temporarily remove the programs which is not currently required and bring the requested programs into memory. This is what we have been seeing. And after that, we have been seeing the difference between logical address and physical address. And CPUs always generates a logical address. Okay, that logical address must be added to the content of relocation register in order to get the physical address. This is what we have been seeing again. And after that, we have been seeing about swapping concept. Okay, what is a swapping in the sense? We need to, whenever a memory is not sufficient, whenever a process needs to be a memory to be executed, a process, however, can be swapped temporarily out of memory to be back in store and brought back into memory for continue the execution. This is going to be called as swapping, and that implies simply remove the processes which is not currently required and bring the requested processes into memory is going to be called as swapping. And we have been seen some of the constraints on swapping. Never swap out a process which is pending for an IO. And please don't try to and please try to see that your all IO operations must be executed on operating system buffers only. Okay, this is, and after that we have been seeing about continuous allocation. Okay, what is this continuous allocation? We have been seeing, whatever the amount of memory which is going to be required to run your program, the memory should be in continuous fashion. And after that, we have been seeing about two concepts: internal fragmentation and external fragmentation. What is internal fragmentation? In the sense, it is the smallest memory hole which can be not accommodated for any one of the waiting processes, which is going to be called as external sorry. And after that, we have been seen about external fragmentation. So what is external? The required amount of memory is available, but it is not in a continuous fashion. Hence, the user cannot able to run the process. Then such kind of a concept is going to be called as external fragmentation. That is going to be called as external fragmentation. Okay, and after that, in order to overcome this particular problem, we have been used compaction technique. Okay, compaction is a process of moving all your process segments or program segments from one particular area to another area so that make it as a single memory hole is empty. This is what we have been seeing in the last class. This is just a small review about what we have been done in the last class. And coming to the today's very important topic is that virtual memory. Okay. So what is virtual memory? A virtual memory is a concept which gives an illusion to the programmer that he has a large amount of main memory, relatively having a small amount of memory. Even though if you're having a small amount of memory, it gives you a look and feel that you have a large amount of memory. That such kind of a concept is going to be called as virtual memory. So what is virtual memory? Now we're going to see. It is a concept used in large computer systems, which permits the user to develop programs as if he had a very large amount of main memory. Let us take an example. Already I have been told you in several times, the basic principle is that whenever the user is trying to execute any particular program, first of all, the program should be copied into main memory. Whenever the user is trying to execute any particular program, first of all, the program should be copied into main memory. Suppose, let us take an example, if the main memory is sufficient for running your program, there is no problem. In case if the main memory is not sufficient to hold your program, then we're going to use the concept of virtual memory concept. Let us take a small example of this. Okay, now suppose we have a main memory capacity of 20 MB. I want to run a program which requires only 8 MB of space. So, okay, 8 MB of space. Okay, now, so 8 MB is okay, it is enough to accommodate in 20 MB so that this will not going to cause any problem at all, so that it will run. Suppose if I want to run a 25 MB of program, I want to run a 25 MB of program, but the memory available is only 20 MB. How can we run? So we can run this 25 MB by fitting on 20 MB of main memory. So once a 25 MB program is run, the people are thinking, the user or programmers are thinking that there is 25 MB of memory is available, but there is only 20 MB is available. That implies it gives an illusion to the programmer that he has a large amount of memory which is having less amount of memory. Okay, that's why we have to define it as virtual memory is a concept which gives an illusion to the programmer that he has a large amount of memory relatively having a small amount of memory. Now let us take an example. Suppose you haven't written one big program. That program is a collection of functions and one main program. Okay, in order to run that particular program, you required 25 MB of main memory capacity is required, but the total available main memory is only 20 MB. How we are going to run this? So now, can you observe it? You cannot run the whole program at the same time. The program execution is always starts at main. So what I'm going to do is that, okay, first of all, I'll copy the main program into main memory. While executing this particular main program, whatever the functions it has been invoked, it is going to be brings at the time of execution by using dynamic loading and dynamic linking, and it is executed. Once its importance has been completed, simply remove from the memory. By using this kind of technique, I can run a 25 MB program by fitting on only 20 MB of memory. That's it. It is over. Okay. So how it is practically implemented? In order to implement this virtual memory concept, okay, we have two methods. Number one, paging. Number two, segmentation. Another mixing approach is, okay, a segmentation with paging. What is this one? So by using this particular paging, segmentation, and segmentation with paging, I can run a large program, okay, with less amount of main memory. Okay, that's why an unknown person knows that, oh, this program is run, that implies this much of memory is available, but the memory available is only 20 MB. So that's why the conclusion of this definition is that virtual memory is a concept which gives an illusion to the programmer that he has a large amount of memory relatively having a small amount of memory. So how can it is practically implemented? Now we're going to see the first technique is going to be called as paging. So paging technique. So what is this particular paging? Okay, so this particular paging concept is demonstrated by means of taking one problem as an example. Okay, why? Because we need to concentrate on more on problems. That's why, okay, I have an entire concept of paging scheme. I have to demonstrate it by using a problem as an example. Let us take an example. Why? Because I need to cover all the problems related to this kind of category. Okay, now we have 4 KB of main memory and I want to run a 8 KB of program. My main memory is having a capability of holding 4 KB of words, and whatever the program I want to run, the program capacity is 8 KB. Just it's double. Okay. Okay. The main memory capacity is only 4 KB. The main memory capacity is 4 KB, and I want to run a program which is of capacity 8 KB. How a 4 KB program now run? Okay, sorry. How an 8 KB program can run by fitting in 4 KB? Now, in order to make this particular process, I use paging scheme. So now, what I'm going to do is that the main memory is divided into blocks or frames, and my virtual memory, or may call it as a logical memory, is divided into pages. The logical memory is divided into pages. Main memory is divided into blocks, or may call it as frames, and virtual memory is divided into pages. The division must be done in such a way that where page size and block size must be always equal. Where page size and block size must be always equal. In this particular case, what I have been done is that I have been divided my main memory into 4 blocks. Okay, 4 blocks. Each one is having 1 KB, and what your logical address space is going to be divided into 8 pages. Okay, each page capacity is 1 KB. So totally main memory is divided into 4 blocks and virtual memory is divided into 8 pages. The division has been done in such a way that where page size and block size is equal to 1 KB, where page size and block size is going to be 1 KB. Okay, whenever the user is trying to execute any particular program, first of all, a program should be copied into main memory. So we have only, okay, 4 blocks are available for running a program. But whatever the program we are trying to run, this particular program requires 8 KB of, okay, 8 pages it is required, 8 blocks it is required. So what I'm going to do is that whatever the current pages which is going to be required, it should be first of all copied into main memory. And once its importance has been completed, it is removed from the memory. And whatever the requested page is currently required, it is going to be bring back into main memory. This is what I'm going to do. Okay, the maximum number of pages that can be allowed in main memory is only 4 pages. Now we'll see some technical things. The total capacity of your main memory is, okay, 8 KB of words. 8 KB in the sense that is 8 into 2 to the power of 10 words. 8 into 2 power 10 words. 8 in the sense 2 cube, and this is 2 power 10. 1 KB in the sense 2 power 10 bytes. So 2 cube into 2 power 10, that is 2 power 13 words. Okay, whatever the program I am trying to run, this program is of capacity. This program is of capacity 2 to the power of 13. In order to represent each and every word, okay, in main memory, so in order to represent each and every word in, sorry, a small change. In order to represent each and every word, okay, okay, now so 2 cube into 2 to the power of 10, that is totally 2 power 13. Okay, in order to represent each and every word in, okay, virtual memory, we require a 13-bit address. A 13-bit address is required to identify each and every word in logical memory. But the physical memory capacity is only 4 KB. 4 KB in the sense 2 square into 2 to the power of 10. Okay, that is 2 power 12. In order to represent each and every word, I require only a 12-bit address. In order to represent each and every word, I require a 12-bit address. Okay, for representing each and every word in memory, and in order to represent each and every word in the virtual memory, or may call it as logical memory, which is of 13-bit. Why? Because 2 cube into 2 to the power of 10, that is 2 power 13. That's it. Okay, now the set of all, okay, physical addresses is going to be false, a physical address space. The set of all logical addresses are going to be called as a logical address space. Now, Totally, we have been divided main memory into 4 blocks. Okay, the main memory is divided into 4 blocks, and virtual memory is divided into 8 pages. 4 blocks in the sense. Okay, 4 blocks in the sense, in order to represent, in order to identify each and every block, we require a 2-bit address. That implies a 2 square. 4 blocks in the sense 2 square. In order to represent each and every block, we require a 2-bit address. So block addresses are 0001 1011. Okay. In similar manner, the total number of pages is 8 pages. 8 pages in the sense 2 cube. In order to identify each and every page, we require a 3-bit address. We require a 3-bit address. That is, the first page address is 000. Second page address is 001, 010, 011, 100, 101, 110, and 111. Okay, and this is going to be called as in order to represent each and every block, we require a 2-bit address. In order to represent each and every page, we require a 3-bit address. Now, whatever the program we are trying to run, that program is of capacity 8 KB. In order to represent each and every word, we require a 13-bit address. But this particular program should be copied into main memory, which is having a capability of holding only 12-bit address. So at the time of execution, you need to convert this particular 13-bit address into a 12-bit address. That is going to be known as mapping. So at the time of execution of a particular page, every 13-bit address is going to be converted into a 12-bit address. The conversion of 13-bit address into a 12-bit address is known as mapping. The conversion of a 13-bit address into a 12-bit address is known as mapping. Now we're going to see how it is going to be done. So all of you see this particular one. Now my main memory capacity is 4 KB. So 4 KB in the sense. So okay, I have been divided this particular main memory into 4 blocks. Okay, the main memory is divided into how many blocks? 4 blocks. So now let us a small change. I'll make it as this is block 0. This is block 1, and this is just wait a moment of time. I'll make a small change in this. This is block 0. This is block 1. A small correction in this. This is block 2. This is block 3. That's it. Now we can go. Now you can observe it. The total main memory is divided into 4 blocks, or we call it as frames. That is named as block 0, block 1, block 2, block 3. In order to identify each and every block, we require a 2-bit address. The address of block 0 is 00. This is 01. This is 10, and this is 11. And similar manner, okay, and the 4 KB in the sense 2 square into 2 to the power of 10. That is 2 power 12. So in order to represent each and every word in this main memory, we require a 12-bit address. In order to represent each and every word in main memory, we require a 12-bit address. We require a 12-bit address. Now coming to the next one, virtual memory. I want to run a program which is capacity of 8 KB. Now I have been divided this particular 8 KB into how many? 8 pages. In order to represent each and every page, I required a 3-bit address. The first page address is represented with 000. Second page address is 001, and the third page address is 010. So on up to like this. Now, in order to represent that is total memory capacity of 8 KB. That is 2 KB into 2 to the power 10. So in order to represent each and every word, we require a 13-bit address. We require a 13-bit address. Now, so correspondingly, we are not having enough space for running these 8 pages at a time. Your main memory is having a capability of holding only 4 pages at a time. So at the time of execution, what are the pages which is currently required? Please try to copy that particular pages into memory. And once the need is complete, remove it and bring the requested page into memory. Now, how do you know that what are the pages which is currently resident in memory and what are the pages which is not currently resident in memory? So, first of all, you must know that which pages are going to be currently resident in memory and which pages are not currently resident in memory. How do you know this particular one? Okay, now we have a page table. We have a page table. We have a page table. What is this particular page table? Okay, the page table simply tells that whatever the pages that is currently required, okay, that particular pages is available in which block number. This is going to be determined by page table. The page table is constructed with only two columns. That is, one is page number and second one is presence bit. This is going to be called as presence bit. Okay, okay, and this is your page number and this is going to be called as your block number. Okay, these are the pages currently required. This particular pages is available in which block numbers, which is going to be represented here. That's it. Now you can please see that page 0 is not available in memory. Page 1 is available in memory at block number 11. Page 2 is available in memory at block number 0. Page 3 not available. Page 4 not available. Page 5 is available in memory at block number 1. Page 6 is available in memory at block number 2. And page 7 is not available. And page 7 is not available. This is how the page table. Now you please try to see that there is how many pages are currently resident now. 1, 2, 3, 4. There are 4 pages are there. Okay, that's it. Now how it is going to be executed? How a 13-bit address is going to be converted into a 12-bit address. How a 13-bit address is going to be converted into a 12-bit address. So clearly says that CPU is always generates a logical address or may call it as virtual address. And CPU always generates a logical address or may call it as virtual address. Okay, this virtual address or logical address is consisting of 13-bit address. This is of 13-bit address. This particular 13-bit address is divided into two parts. Number 1, page number. Number 2 is offset. Number 1 is page number. Number 2 is offset. Okay, CPU always generates a logical address. That logical address is consisting of page number and as well as offset. The page number is simply is applied to page table to determine whatever the page currently you requested, which is available in which block number. Now, the current page which is requested by the CPU is 101. So, this 101 is available in memory at block number 01. It is available in block number 01. Now, this particular 01 along with the presence bit is supplied. Now, this offset, whatever the offset has been left over here, this offset is going to become here and these 2 bits is come here. Total combined together it is of 12 bits. Total combined together it is of how many bits? It is 12 bits. Now you are directly referring to the block 01 and you are executing here. And that is whatever the page you are requesting for page 5, the page 5 is available in block number 1. So that correspondingly this is going to be executed. You please try to observe that this is a 13-bit address. Now it is going to be converted into a 12-bit address. This kind of a process is known as mapping. Okay, the conversion of 13-bit address into 12-bit address is known as mapping. So that what is okay, this CPU generates a logical address which consisting of page number and as well as displacement, or we call it as page number and offset. The page number is simply sent to the page table. The page table simply determines whatever the page you requested that is available in which block number. The block number is attached to this particular offset in order to get the 12-bit address. The block number is attached to this offset in order to get the physical address. Okay, this is how it is going to be executed. Now, currently, whatever the page you are requested, it is available in memory if it is no problem. But whatever the page currently requested, if it is not available in memory, then immediately it gives you an error message, page fault occurred. Whatever the page currently requested, if the page is not available in memory, then immediately CPU gives an error message, or operating system gives you an error message that page fault occurred. So whenever a page fault is encountered, what you need to do? You need to bring that particular page into main memory. You need to bring that particular page from secondary storage device to main memory. In case if there is enough space, okay, this is also we termed as demand paging. At the latter time, we will see this concept as a demand paging. Now, currently, what page you are requested in order to bring that particular page into memory, if there is enough space, okay, at least one block is free so that we can copy that particular page into memory. But what happens is that whatever the page you are requested, if it is not available, there is no enough space for storing that particular page into memory, then you need to remove one of the block. You need to remove one of the page which is not currently required in memory and bring the requested page into memory. So currently, whatever the page you are requested which is not available in memory, it immediately gives you an error message. Page fault occurred. Let us take. I am referring for 100 page. I am referring for 100. But 100 page is not available in memory. So I need to bring that particular 100 page into memory. But there is no space. Why? Because how many pages are already resident in memory? 1, 2, 3, 4 pages are already resident in memory, so that I cannot accommodate for this particular page 4. Then what I need to do is that I need to remove one of the page, that is page 1 or page 2 or page 5 or page 6, any one of the page I need to remove. I need to bring the page 4 into memory. Now, so this kind of a technique is going to be handled by page replacement algorithms. That is done by page replacement algorithms. So let us see the final discussion. Okay, CPU generates a logical address. That logical address is consisting of page number and as well as offset. The page number is sent to the page table. The page table simply determines whatever the page currently are requested, which is available in which block number. The block number is going to be attached to the offset in order to get the physical address. Okay, and whatever the page currently are requested, if it is not available, then immediately it will give an error message, page fault occur. Whenever a page fault is encountered, okay, you need to bring that particular requested page into memory. Okay, how do you bring that particular? If the space is available, then no problem. In case the space is not available, you need to use page replacement algorithms to bring the requested page into memory. Now, so what are the different kinds of page replacement algorithms are there? There are 3 kinds of page replacement algorithms are there. Number 1, first in, first out. Number 2, least recently used. Number 3, optimal replacement. Number 3 is optimal replacement. So let us see first in, first out. What is this first in, first out? Which page is entered into the first in main memory? So please try to remove that particular page whenever a page fault is encountered. First in, first out. Which page is entered into main memory? First, please try to remove that particular page first. That is going to be called as first in, first out. And the second very important one is least recently used. Okay, which page is not going to be used for longest period of time? Which page is not used so far? Which page is not used so far for a longest period of time? Please try to remove that particular page. Okay, which page is not used so far for a longest period of time earlier? Okay, so please try to remove that particular page. This kind of an algorithm is going to be called as least recently used. And coming to the third very important one is that optimal replacement. Okay, so you please try to remove a page which is not currently required in future. So which page is not going to be required for a long time in future? Please try to remove such kind of a page. Which page is not used for longest period of time in future? Please try to remove that particular page. Such kind of a technique is going to be called as optimal replacement. Such kind of a technique is going to be called as optimal replacement. Now we'll take one problem as an example. Now, we'll see all these algorithms and how we are getting the problems, how to calculate the number of page faults. Okay, and they ask you a question like this. Let us take a problem. A virtual memory system has an address space of 8 KB and memory space is 4 KB. You want to run a program. The program is of size 8 KB and the memory space is only 4 KB. The page and block size is they have been given as 1 KB of words. The following page references occur in a given time interval. The CPU is requested for the first page is 4, the next 2, 0, 1, 2, 6, 1, 4, so on up to like this. Now the question is, determine the 4 pages that are resident in memory after each page reference. First of all, you need to determine the first very important question is, determine the 4 pages that are resident in memory after this entire page reference string. This is going to be called as a page reference string. Okay, and you need to calculate the number of page faults. Okay, of when the algorithms according to first in first out, how many page faults? According to least recently used, how many page faults? According to optimal replacement, okay, how many page faults? You need to calculate it. Now coming to the first one, first in first out. Coming to the first one, first in first out. So which page is going to be arrived in memory first? Please try to remove such kind of a Which page is going to be arrived first? Please try to remove that page first. Okay, now let us see. My main memory capacity is now. Hello? Sorry about that. I'll call you back. Okay, now currently my main memory is having a capability. The page size and block size they have been given as 1 KB. That's why the number of pages is 8 and the number of blocks is 4. That implies my main memory is having a capability of holding the maximum number of blocks is maximum number of pages is only 4. Why? Because there is 4 blocks are available. Okay, now that's why first immediately the CPU is requesting for a page 4. So now there is 4 blocks are available now, so that I can put okay, this particular page is not available, so that I'll put this particular page into memory. Okay, next they ask you for the 2. Again, page fault occurred, 2 is not there. Okay, again we have 3 blocks of space I can put. Okay, say 2, and after that again is requesting for 0. So 0 is also not there. Then what I need to do? Still 2 more blocks are free, so that I can put 0 in third block. Okay, again it is asking for 1. 1 is already not there. Again we have space for 1 block. So correspondingly, I can put this particular page 1 in memory. That implies for 201, first 4 pages, we got 4 page faults. So all 4 pages are now copied in memory. So currently, the 4 blocks has been filled with 4201 pages. And after that, CPU is requesting for a page 2. And after that, CPU requesting for 6. After that, CPU requesting for 1. Similarly, 40102357. These are the pages which is requested by the CPU now. The next page which is requested by the CPU is now it is 2. Now 2 is available in memory. Yes, it is already there. Okay, so there is no page fault is occurred. CPU simply execute that particular page. Next up, CPU simply asks you 6 page. 6 is available in memory. Okay, 6 is available in memory. No, so that according to first in first term, I need to remove the page 4 in place 4. I get 6. That's why I indicated with the red number, indicated the red color. That is, you got 1 page fault. That's why I have been removed the page 4 in place 4. Okay, I have got 6. And after that, CPU is requesting for the page number 1. So page 1 is already available in memory. So that's why there is no page fault as it is 6201. Next, the CPU is requested for 4, but the 4 is not available. According to first in, first out, again the next page removed is second page. So next one is removed is 2. So that's why in place of 2, we got 4 here. That is another page fault. Next, the CPU is requesting for a page 0. Page 0 is already available in memory. No problem. That's why 6401 as it is. 1 is already there in memory. Again, 6401 becomes 6401 as it is. Next, it is requesting for a page 0. Page 0 is already available in memory. That's why happen becomes a 6401. Next, the CPU is requesting for page 2. But page 2 is not available. So I need to remove 0. In place of that, I need to get 2. And after that, again, CPU is requesting for 3. 3 is also not there in memory. I need to remove 1. Again, in place of 1, I need to copy 2. Next, the CPU is requested 5. So again, according to first in, first out, again, you need to come back to 6 and you remove the 6. In place of that, you need to place 5. And after that, CPU requesting for a page 7. Page 7 is also not available. So according to first in, first out, you need to remove this particular 4 and 10. So after taking this particular page reference string, what are the pages which is currently required in memory in which order? In the sense 5, 7, 2, 3. This is the first question they have been asked. After referencing this particular page reference string, what are the pages that are currently resident in memory and which order? That is in order of 5, 7, 2, 3. Now, calculate how many number of page faults. Now we calculate how many number of page faults. How many number of page faults in the sense initially first 4 pages you'll got 4 page faults, and after that you'll get 1, 2, 3, 4, 5, 6. 4 plus 6, the total number of page faults is 10 page faults. Okay, this is the question how we got. Okay, so after referencing this particular page reference string, what are the pages which are currently resident in memory? And the second very important point is that, okay, how many page faults? That is 4. and another 6 is indicated by the red number. That is totally 10 page faults. This is according to first in, first out. Now coming to the second very important one is that least recently used. The second very important one is least recently used. So this particular least recently used, please try to remove a page which is not used for longest period of time. Please try to remove that particular page. Which page is not used for longest period of time? Please try to remove that particular page. Now we'll see. Okay, initially the page reference string, initially first 4 pages, 4201. We got page faults. In that we have a sufficient space so that we can copy the 4 pages, 4201. The removal order is also same, 4201. Why? Because whenever a page fault is occurred, I need to remove 4, and after that I need to remove 2, after that I need to remove 0, after that I need to remove 1. So which page is currently referred, which is according to priority, it is high priority, it is always listed in memory. So what are the pages which is currently referred, which is added at the end, and whenever a page fault is encountered, you need to remove the first one. Okay, this is like a queue. This is like a queue. So insertions of new pages are allowed from the rear end, and deletions of the pages is going to be done from the front end. Now let us take next one. The CPU is requesting for page 2. Page 2 is already available in memory. Page 2 is already available in memory. But the recently referred pages, which one? 2. Okay, recently referred pages 2. So that in removal order, the 2 is going to be the last priority. Whenever a page fault is occurred, you need to remove page 1, page 4 first, and after that 0, and after that 1. The last priority is for 2. Why? Because the currently referred page is always a high priority. The currently referred page is always high priority. The next page referred by CPU is 6, but 6 is available in memory? No. Then page fault occurred. So according to page fault, what you need to do? You need to remove the first one. Which one? 4. 4 has to be in place of 4. You got 6. Now 6201. So now in removal order, the 4 is removed. 012. The recently entered page is 6. That is going to be appended at the end of the list. So this is again the next page referred by the CPU is 1. That is 6201. Okay, 1 is already there in memory, but the priority order is changes. So the 1 is recently referred. That's why 1 is coming from this place to last place. Again, the CPU referred a page, call it as 4, but the page 4 is not available in memory. Page 4 is not available in memory. You need to remove a page. Which page you need to remove? 0. In place of that 0, you will get 4. So that in removal order, the 2 is 6, 1, and the last one is 4. And coming to the next one, the CPU referred a page 0, but 0 is not available in memory. Which page you need to remove? 2. So that in place of 2, you are getting 0. Now removal order 614, the recently referred one is 0. 0 is being placed at the end. Next 1. So the currently referred page is 1. It is already available in memory. So what happens is that in removal order, 1 is going to be placed at the last. Again, CPU referred a page 0, but 0 is already available in memory. No page fault. But in removal order, 0 is going to be placed at the end. Again, the CPU is referred for a page 2. 2 is not available in memory. So that you need to remove first one, 6. In place of 6, you need to get 2. In removal order, 410. Recently added one is 2. It is appended at the end. And 3. So 3 is already not there in memory. So that you need to remove 4. In place of 4, you need to get 3. And after that, again, in removal order, 3 is at the end. Again, CPU referred a page 5. 5 is also not available. So you need to remove page 1. In place of 1, you need to get 5. And after that, now removal order 5 is going to be entered at the end. Now last page referred by the CPU is 7. So 7 is not there. So you need to remove 0. In place of 0, you need to get 7. 2735. Now removal order 7 is appended at the end. Now after making this particular page reference string, now after making this particular page reference string, okay, so what are the pages which is currently required in memory? 2735. Okay, this is the order we have. The number of page faults is initially 4. 1, 2, 3, 4, 5, 6, 7. 4 plus 7. Totally, the number of page faults according to least recently used is 11. In a similar manner, we are also having Optimal replacement algorithm. In optimal replacement algorithm, just a slight change the definition. Which page is not used for longest period of time? Please try to remove such kind of a page. Which page is not used for longest period of time? You need to remove that kind of a page. So you please try to know the page reference team well in advance. So that what are the pages we need to remove is which pages you need to remove, and you need to see the rest of the page reference stream. Which page is not used for longest period of time? Please try to remove such kind of pages. In a similar manner, you can do it. You will get the number of page faults is only 9. You will get only number of page faults is 9. Is it clear, everyone? So we have been seen about 3 algorithms. Number 1 is first in, first out. Which page is first arrived into the computer system? Please try to remove first that page. Please try to remove that page. And second very important one is the LRU. Please recently use. And which page is not used for longest period of time? Please try to remove such kind of a page. And the third one, which page is not used for longest period of time in future? That is called it as remove that page, which is called as an optimal replacement. This is how we are going to see the paging concept. Now we'll go in theoretical manner. Now we have been seeing this entire paging concept in the form of problematic. So how you get a problem? How problem will going to be arises? What kind of questions they ask? We'll have been seen. Now we'll see the concept. Okay. Now all of you please try to understand this particular concept. So paging concept. What is paging? Okay. Now the CPU is always generates a logical address. The CPU is always generates a logical address which is consisting of page number and as well as offset. Page number and as well as offset. The page number is simply sent to the page table. The page table simply determines whatever the page you are requesting that is available in which block number, or may call it as frame number. The frame number is attached to the offset in order to get the physical address. In order to get the physical address. Is it clear? Okay, once we go back to this particular slide, then you observe this in this. Okay, so CPU generates a logical address which consisting of page number and as well as offset. The page number is simply sent to the page table. The page table simply determines whatever the page you currently are referring, which is available in which block number. The block number is attached to the offset in order to get the physical address. That is what I have been shown in this diagram. Okay, the CPU generates a logical address. The logical address is consisting of page number and as well as offset. The page number is sent to the page table. The page table simply determines whatever the page you are requesting that is available in which block number or the frame number. This frame number is attached to the offset in order to get the physical address. That's it. This is how it is going to be happening. Now we'll see. Okay. For better understanding, okay, my logical memory is having the 4 pages: page 0, page 1, page 2, page 3. So then, and my main memory is having 8 blocks. Okay, main memory is having 8 blocks. Okay, here this is block 0, block 1, block 2, so on up to like this. And the page table is represented like this. Page 0 is available in block number 1. This is how do you write a page table. The page table simply, I am telling. So page 0 is available in block number 1. Page 1 is available in block number 4. Page 2 available in block number 3. Page 3 available in block number 7. This is how to represent a page table. Already we have been seeing this kind of a concept here like this. With mathematical way, we have been seeing page 0 is not available. Page 1 available in memory at block number 3. Page 2 available in block number 0. Page 5 available in block number 01. Page 6 is not available in memory at 10. And page 7 is not available in memory. Like this we have been seeing. Now, coming to the next very important one is, okay, structure of a page table. The next very important one is, okay, we have how this page table is going to be adjusted and where this particular page table is generally stored in memory. Okay, in order to store this particular page table, why? Because this particular page table is going to be frequently referred by your CPU. Always CPU refers that whatever the pages that is currently requested, it is available in which block number. Every time you need to search it in okay, page table. So if you try to put that particular page table in registers, what happens is that it works very faster. Why? Because in our computer system, what is the fastest memory? Register. The first place is always goes to register. Second place is cache memory, and third place is main memory, and fourth place is secondary storage devices. So, in case if we try to implement the page table in registers, it works very fast. It works very fast. It works. It works very fast. Okay, but what the problem is that your computer system is supports only a less number of the registers, so that the entire page table cannot be accommodated in registers. Okay, the second very important concept is that the page table is implemented on as a set of dedicated registers. These registers should be built with high-speed logic to make the paging, addressing, translation efficient. If the page table is large, then the table kept in memory. Okay, then if the page table is large, we cannot accommodate the entire page table in register. Then what we're going to do is that the entire page table is put it in memory. Currently, which pages are going to be referred, that particular page base value and limit values are going to be stored in register. Okay. Okay. So we have, okay, in case the entire page table is not enough to hold in registers, then we are going to be hold that particular one in main memory, and currently which pages are referred by your CPU, that particular two pages, that particular page base register value, limit register value is going to be placed on registers. That's it. This is what is good. This is PTBR stands for page table base register, page table limit register. That's it. This is what is going to be called as and this one. This is second way of implementing. And the third one, where your page table is implemented, you can also put the page table in cache memory. Why? Because your second fastest memory in your computer system is the second fastest memory in your computer system is page table. Sorry, cache memory. So that if in case if you try to implement the page table concept in cache memory, then such kind of a concept is going to be called as translate look-aside buffers. That is going to be called as translate look-aside buffers. So before going to the detailed discussion about the working behavior of TLBs, translate look-aside buffers, first of all, you must know that the working behavior of cache memory. You know that already. The cache memory is the second fastest memory in your computer system. The cache memory is the second fastest memory in your computer system. It is placed in between CPU and main memory. Whenever the CPU want to read any particular word, first of all, it checks that whether the word is available in cache memory. Okay, whenever the CPU want to read any particular word, first of all, it checks that whether the word is available in cache memory. If the word is available in cache memory, then it simply gets it and executes it. If the word is not available in memory, it goes to main memory. It brings a block of instructions containing that instruction and copy it back onto cache memory. From the cache memory, only going to be CPU read the instruction. So whatever the word you're searching, if the word is available in cache memory, then it is going to be called as hit. If the word is not available in cache memory, then it is called as miss. So whenever a miss is encountered, the CPU is going to be posed to main memory, brings a block of instructions containing that instruction, copied back onto cache memory, and from the cache memory, the CPU is going to execute the rest of the instructions. This is how it is going to be happen. This is how it is going to be happen. Now, how do you measure the performance of a cache memory? The performance of cache memory is measured in terms of hit ratio. What is a hit ratio in a sense? Hit ratio is simply defined as number of hits by number of hits plus number of misses. Number of hits by number of hits plus number of misses. Now, correspondingly, so in case the page table is implemented in cache memory, if the page table is implemented in cache memory, now correspondingly, that kind of a concept is going to be called as translate look-aside buffer technique. Okay, now what is this translate look-aside buffer technique? CPU generates a logical address that consisting of page number and as well as offset. The page number is simply sent to the page table entries which is currently residing in cache memory. So the entire page table is not sufficient to hold in where? Cache memory. So what are the most frequent pages which is referred by the CPU will going to be placed on cache memory, which is called as TLB, translate location site buffer. So whatever the page currently you requested, first of all it checks that whether it is available in cache memory. If it is available in cache memory, in which frame it is available, that frame number and this offset, that frame number and this offset is going to be attached in order to convert a logical address into a physical address. This is how it is happening. But whatever the page currently requested, it is not available in cache memory, then it is called it as TLB miss. Whatever the page you are requested, if it is available in cache memory, then it is called it as TLB hit. In case whatever the page currently requested, it is not available in cache memory, it is called as TLB miss. Whenever a miss is encountered, whatever the page you are requesting, it is searched in page table registered in memory, and you search it and update the entry in page table in cache memory, and the particular frame number is updated attached to your offset in order to get the physical address. And this kind of a concept is going to be called as this kind of a concept is called as TLB, translate location site buffer technique. Now coming to the next one, protection. What do you mean by protection? Now whenever a page fault is encountered, you are bringing that particular page, this demand paging, into main memory. Where you need to copy, wherever available, you need to copy there. But how do you know that which frames are already occupied by which pages? Which frames are now currently free? How do you know that? In page table, we have an entry called it as presence bit. Already we have been seen in the earlier. This is what is going to be called as presence bit. This is 0 in the sense, this page is not available. 1 in the sense, this particular page is available in block number 3. In a similar manner, so page 0 is available, valid, is valid. It is there in memory at block number 2. See, page 0 available in block number, page 1 is available in block number 3. Page 2 available in block number 4. Page 3 available in block number 7. Page 5 available in block number 9. Page 6 is not available. Page 7 is not available. Invalid, invalid. These pages are not there. So whenever they want to bring one particular page into memory, first of all, we see that which pages are currently free and which pages are currently empty, so that in that free space area, we are going to bring that particular page. We are not simply overlapping one page by one page. That is simply, I can conclude this topic by using the protection is done by using valid or invalid bits. You may also call it as this is presence bit. Now coming to the next one, multi-level paging. Multi-level paging. What do I mean by this multi-level paging? The page table itself is also page. You understood my point? The page table itself is also paged. What is the meaning of this? Let us take an example. I am taking a 32-bit machine with a page size of 4 KB. Let us take 32-bit machine. That implies the total available addresses is 2 power 32. In order to represent each and every word in memory, we require a 32-bit address. Is it clear, everyone? In order to represent each and every word, we require a 32-bit address. But the page size available is 4 KB. 4 KB in the sense, page size available is 4 KB. 2 square into 2 power 10. In order to represent each and every page, I require only 12-bit address. 12-bit address. I require only 12-bit address. Now, a logical address is divided into a page number consisting of 20 bits, a page number consisting of 20 bits, and a page offset of 12 bits. Sorry, a small error in this. You need to write 12 here. A small mistake. This is 12. Let us we'll see to make a correction on this. Okay, so the page number is totally of 20. Okay, a page number consisting of 20 bits, and page offset is defined as 12. Page offset is defined as 12. Why? Because I have been given 4 KB. 4 KB in the sense 2 square into 2 to the power of 10. That is totally 2 power 12. Okay, and this one 20. Now we the page table, the page number is further divided into a 10 bit and 10 bit, the page number. So the page number is totally 20 bits and page offset is 12. Why? Because it is 4 KB of space. That's why I have been divided as offset, and the page number is 12 bits. This 12 bits is now divided into 10 bits. Okay, so divided into 10 page number and 10 bit offset, and this is 10 bit page number and this is 10 bit page offset. Now we have a page table. For this page table, we are having another page table. Okay, so outer page table simply determines whatever the page which is requested, it is available in which block of pages. This page table simply determines, okay, whatever the page currently you requested, that is available in which block number. Is it clear? That's it. So that implies CPU generates a logical address that consisting of page number and as well as offset. In this page number, it is 20 bits. This particular 20 bits is going to be divided into 10 and 10. The first 10 bits is sent to the outer page table. The outer page table simply determines whatever the page you are currently requested, which is available in which block of pages. That page offset is going to be written. Using that particular offset, you are taking the second 10 bits together with your user to determine whatever the page currently you requested, that is available in which block number. That implies you're simply maintaining a page table for a page table. Hence, it is going to be called as multi-level paging, or may call it as two-level paging. In this particular case, it is a two-level paging. You may call it as multi-level paging. Now, so coming to the next very important one is that, so let us take a small example, okay, for a better understanding of a student. So if you take a Java complete reference textbook, in the first page, we have index 1. Chapter 1, introduction. Chapter 2, something control structures. Chapter 3, arrays. And so on, they give you the chapter names. If you go for the second page, you have another index. That index simply shows that in 1.1 what you have, 1.2 what you have, the detailed context. The first page simply give you a glance and second page give you the list of the topics. In a similar manner, we are also having a multiple page tables. So that implies we are maintaining the page table itself is also page. Such kind of a concept is going to be called as multi-level paging. Such kind of a concept is going to be called as multi-level paging. Now, coming to the next very important one is inverted page table concept. The next important one is inverted page table. Okay. What is this inverted page table concept? An inverted page table has one entry for each page in of memory. Each entry consists of a virtual address of the page stored in memory location along with the process information also. Already everyone aware that in a computer system there is not only one process is running, there are multiple processes running. This concept we are already referred as multi-programming. So in a multi-programming, more than one process can be simultaneously reside in main memory, and during the execution of one particular process, in case if any process requires an IO operation, the CPU does not sit idle, it simply switches from one particular job to another job. Now there are multiple processors running in my computer system. Point number 2, how can the operating system can identify each and every process that is running in your physical memory or main memory? How can an operating system can identify each and every process? The operating system is going to identify each and every process by using a process ID number. The operating system is going to identify each and every process by using process ID number. Okay. So how can it is restoring the status of a particular process? By using PCB, process control block. Already this topics are already been dealt. Okay. It is done by using process control block. Now, each and every process is going to be identified by a process ID number, which is one of the part of a process control block. There are several processes running. Each and every process may have sufficient space, may not have a sufficient space. If a sufficient space is there, it is not any problem. In case the process is not having the sufficient space, in order to run that particular program in a require, you require virtual memory concept. Once you want to run the program, even though if you are not having enough space for running the program, you are using virtual memory concept. So once if you haven't used virtual memory concept, you need to maintain a page table. Every process has to be maintain a page table. Every process has to be maintain a page table. Okay, now in that, how can the CPU can knows that which process currently I'm executing? In that particular process, which page currently I'm executing? How can an operating system can remember all these particular things? This can be done by using inverted page table concept. This can be done by using inverted page table concept. What is this inverted page table? CPU generates a logical address. Earlier it consisting of only page number and offset. Now along with that you're also having process ID number. CPU generates a logical address. That logical address is consisting of process ID number, page number, and as well as displacement. Now process ID number and page number together it is going to be sent to the page table. Process ID number and page number, process ID number and page number the process ID number and page number together with it is going to be sent to the page table. The page table simply determines whatever the page you're requesting on this particular process, which is available in which frame number. Which frame number? The frame number is attached to the offset in order to get the physical address. This is what is happening. Okay, the CPU always generates a logical address. And that logical address is consisting of page number and as well as offset. Along with that, additionally we having process ID number. The process ID number, page number, along with that it will send it to the page table. The page table simply determines whatever the page currently you are referring. That page is available in which block number. The block number is attached to the offset in order to get the physical address. And coming to the next one, shared pages concept. What is this particular shared pages concept? A process may share a common pages. A process may share a common pages. There is no problem. In case if it is a read-only program, okay, it can be shared by any number of processes at the same time. Why? Because the data will not going to be lives in inconsistent state. Read-only programs can be shared by any number of processes at the same time. Now we observe it. Process P1 is running in running an editor program which is resides in 3 blocks and works on data 1. And process P2 is also running same editor program which is resides in 346. The same pages has been shared. Process P3 is also running with the same pages 346. Process P1 works with data 1. Process P2 works with data 2. Process P3 works with data 3. Data 1 is reside in page 1, block 1. Data 2 is resides in block 7. Data 3 resides in block 2. Okay, now this particular 3 processes are sharing a common blocks 3, 4, 6. Let us take a small example for this. Suppose if you open an MS Word document, okay, suppose if you open an MS Word document, now you're typing your biodata something. Okay, while typing, okay, your wife came and asked you to type her biodata. Then what you need to do? You need to open another window. In that window, again you need to type your wife's biodata. That implies for running another Word document, no need to run this MS Word software again. This editor program is already running in memory. So in what area which is running, the same area can be used to type your wife's biodata. And your child came, and your child is also asking that, Dad, also type my biodata also. Now you are open another document. So this third document is also not required an editor program to be again recopied into memory, which is already there in 346. Okay, again by running this 346, You can get this. That implies, okay, the person and her wife and son both are sharing editor program common. In first document, they are typing his own biodata. In second document, they are typing their wife's biodata. And third one is son's biodata. This is that implies. That's why. Can you remember one point? Okay, in process management, I told you process. A process can be thought of as it is a program and execution. In order to execute, sir, okay, execute that particular process while copying into memory. After copying into memory, the total process is divided into two parts. Number one is text section. Number two is data section. Okay, this is text section and this is data section. The text section contains the total machine language translation of the source program, and data section contains the list of all variables I told. Here in this particular case, the text section contains editor program, which is read only, and the data section contains whatever the data you are typing, which is going to be called it as data section. That is the reason why the process, okay, while executing, it is divided into two sections. A process while executing, it is divided into how many sections? Two sections. Number one is text section. Number two is data section. This is what is the paging concept. Is it clear, everyone? Okay. Now we move on to the second type of virtual memory concept implementation. The second. So in order to implement a virtual memory concept, we have, okay, two major techniques. One is hybrid technique, one is paging, second one is segmentation. Okay, now we finish about paging. Now from the observation from the earlier example, you can understood that in paging scheme, the user view of memory is not the same as actual physical memory. Why? Because what I told in the example, suppose you written a program with 10 functions, one main program. Okay, while before whenever the user is trying to execute any particular program, first of all, the program should be copied into main memory. So if the main memory is not sufficient, first of all, main program is going to be copied. While executing that particular main program, in case if any function is invoked, that function is copied at the time of execution according to dynamic loading and dynamic linking. Once it is executed, it is removed. Like this we have been told. But in paging, we are not done like that. In paging, your total entire program is divided into pages, and currently the main program is contained in which pages, only that pages are copied, and while executing that main program, which function has been invoked, only that function pages has been copied, and once its execution is complete, it has been removed from the memory. This is what is done. That's why the main disadvantage of paging scheme is that the user view of memory is not same as the actual physical memory. The user view of memory is not exactly the same as the actual physical memory. But in segmentation, the user view of memory mapped onto physical memory. The differentiation between logical memory, okay, the mapping is only the technique which allows the differentiation between logical memory and physical memory. Now we'll see. Okay, so segmentation is one of the basic techniques which completely supports a user view of memory. Basic technique. That is the first one, and this is first. So what the disadvantage we are facing with paging scheme? In paging scheme, the user view of memory is completely separate from actual physical memory. The second disadvantage is that paging scheme suffers from internal fragmentation. Suppose let us take an example. I want to run a program which is of 250 lines, but each page size is defined as 100 lines. Then what happens is that I require 3 pages. First page is 100 lines full, second page is 100 lines full, and third page occupies only 50 lines, and whatever the 50 lines which is left over in the third page, it's simply wasted. It cannot be used for running any other programs. You know that what is internal fragmentation? It is the smallest memory hole which cannot be accommodated for running any one of the process. That implies whatever the memory space which is left over in the page, it cannot be used for running any other pages at all. That's why the paging scheme suffers from internal fragmentation. In order to work on this kind of a problems, next we have been entered into a second kind of memory management scheme is that segmentation. So first very important thing is that the segmentation is completely supports the user view of memory. Okay, it is completely supports for user view of memory. Whatever the program you want to run, the program is going to be viewed as it is a collection of segments. So first of all, whatever the program you want to run, that program is going to be viewed as a collection of segments. Each segment is having a variable length. Each segment may have a variable length. Each segment is having a variable length. Let us take an example. A segment is a logical unit such as main program and what functions you have been written, what stacks you have been written, what is your symbol table. So main program is treated as one segment. So whatever the functions you have been written, every function is treated as one segment. And symbol table, what is symbol table? It is generated during pass 1 and it is used in pass 2. That is also one segment. Stack, what is the need of stack? Before switching from one particular function to another function, first of all, you need to save the status of the current function where it has been stopped somewhere in the stack, and you need to resume the status of that particular function at a later stage. Okay, this is also going to be called as one segment. That implies in order to run your process, what are the various components? Okay, you are going to be using each and every one is going to be called as one segment. Each element in the segment are identified by their offsets. Each and every segment is having some segment numbers, and each and every segment is identified by a segment number. Page number, and every word in the page is identified by offset. In a similar manner, whatever the segments you are running, each and every segment is identified by a segment number, and every element within that segment, okay, is identified by okay, offset. So each and every segment is identified by offset. So that is, a logical address space is a collection of segments. Each and every segment, in order to, okay, now we'll see this one by means of an example. So I'm taking my logical address space is a collection of segments. I'm taking 5 segments. My main program is one segment, and square root is one segment. The symbol table is one segment, and stack organization is one segment. Subroutine is one segment. Totally I have been considered 5 segments. Now, how can you protect this particular segments? So already I told that each and every segment is identified by a segment number. Every element in that segment is identified by a segment offset. Every element is identified by segment offset. Now, how can you protect one segment addresses with another one? Already you know that the protection is done by using base comma limit register. Here also we are having every segment is having base value and as well as relocation value and offset, every limit value, both are there. By using the base and limit, okay, we can protect each and every segment. So one segment addresses should not be overlapped with another segment addresses. Okay, this is, now we're going to see this example. Now each and every logical segment, each and every logical address is consisting of minimum 2 parts. Each and every logical address is consisting of minimum 2 parts. Number one is segment number and offset. Similarly, like page number and offset. Already I told you in the paging scheme, each and CPU generates a logical address which consisting of page number and offset. In a similar manner, here also in segmentation, CPU generates a logical address which is of segment number and as well as offset. Now, okay, in that now we have a segment table. What is this particular segment table? Earlier we have a page table in paging scheme. In page table simply determines whatever the pages currently you are referred, that particular pages are available in which block numbers. In a similar manner, currently whatever the segments you are referring, whether the segment is available in memory or not, if it is available, what is its base value, what is its limit value? Why? Because while executing the particular segment, whatever the addresses you have been generated, these addresses must be lies between greater than or equal to base and less than or equal to base plus limit value. You cannot access other addresses. Okay, that is segment table. So segment table simply tells that whatever the segments currently you refer, that segment is available in memory or not. In case it is available, it simply returns you what is the base value of the segment and what is the limit value of the segment. In order to improve the efficiency of an execution, in order to improve the fastest, in order to improve the fastness, okay, we use segment table base register and segment table length register. These two values, currently which segment is referred, these two values are going to be placed on the segment table base register and segment table length register. Okay, that's one. And after that, how protection is going to be done? Okay, earlier we have been seen that protection is done through presence bit, or may call it as valid or invalid bits. In a similar manner, in segment table, we're also having valid or invalid bits. Okay, valid or invalid bits. By using this particular invalid or valid bits, you can provide security for your segment. And you please try to see that, okay, whatever the segments which is already there in memory, okay, that particular memory space should not be occupied by someone. Anyway, this particular protection is already done through base comma limit. This one. Okay. Now, similarly, how we are going to be sharing the pages, segments is also can be shared. There is no problem. Okay. Code sharing of occurs and a segment levels also. Now, since the segments are vary in length, okay, we cannot each and every segment occupies a different length of memory. Each and every segment is occupies a different length of memory. Depending on that, so memory allocation is dynamic. So that is a storage allocation problem. Okay, the first of all, whenever a new process has to want to enter into memory, first of all, you need to identify whether we have an enough hole for copying this particular segment into memory. Whether we have a enough hole to copy into memory. Then, and in case if enough hole is there, whether it is allowed or not, we will see. Now, again, we will got internal fragmentation and external fragmentation problems will be vectored in segmentation. Okay, already you know in continuous allocation I told what is internal fragmentation in the sense that it is the smallest memory hole which cannot be accommodated for running any one of the waiting process. Which is going to be called as internal fragmentation, and external fragmentation in the sense the required amount of memory which is available, but it is not in a continuous fashion, hence the user cannot able to run the program. That situation is going to be called as external fragmentation. Okay, in order to overcome this, okay, we have first bit, worst bit, and last bit algorithms are there. You can use that particular dynamic storage allocation techniques, and you can do it. Now we'll see the hardware implementation of segmentation. The hardware implementation of segmentation. The CPU is always generates a logical address that consisting of segment number and offset. The CPU is always generates a logical address that consisting of a segment number and as well as offset. The CPU generates a logical address that consisting of segment number and as well as offset. The segment number is sent to the segment table. The segment table simply retrieves the limit and base value of the currently referred segment. Okay, CPU generates a logical address which consisting of segment number and offset. The segment number is sent to segment table. The segment table simply limit and retrieves limit and base value of the currently referred segment. And first of all, it retrieves limit value. Whatever the offset you have been written, the offset value should not be crosses this limit value. In case if it is crosses, then you are trying to access some other segment addresses. That is immediately it gives you an address error. That is trap. Trap is nothing but an enter. It is an address error. Okay, whatever currently you are executing, you are not referring the current address, you are referring some other one, legal, immediately it gives an address error. But whatever the offset you have been written, if the offset is less than is limit value, in order to get the physical address, content of base register plus this offset is added together in order to get the physical address. In order to get the physical address. Now we understood CPU generates a logical address that consisting of segment number and as well as offset. The segment number is sent to the segment table. The segment table simply refers, currently whatever the segment you are referring, whether the segment is available or not, If the segment is available, it simply retrieves what is the limit value of the segment. This offset, whatever you have been generated, this offset should be less than this limit value. Otherwise, it will give you a trap or an interrupt, simply block the execution. This, in order to get the physical address, this offset is added to the content of base register in order to get the physical address. Is it clear? That's it. Why we have been dividing the address into like this, base, comma, limit, like this. Already you know that there's a relocation, compaction. Okay. In case you want to relocate a process from one particular memory area to another area, you need not change each and every instruction address, which can be done by using simply by changing the content of base register. Simply by changing the content of base register. This is what is there. Now, coming to the next one. How practically we can implement this particular segment table? A segment table can be implemented in registers. The first very important one is a segment table can be implemented in registers. Okay. Why? Because in our computer system, the register is the fastest memory in your computer system. If you try to implement the entire segment table in register so that it will access very fast and your program execution is very fast. But the problem is a segment table kept in a register can be referred very quickly. The addition to the base and comparison with the limit can be done simultaneously to save the time. So we can do this comparison and this addition can be done simultaneously. This comparison and this addition both can be happen at the same time parallelly. No problem. But what happens is that your registers, your computer is having very less number of registers. Your computer is having very less number of registers. You cannot accommodate entire segment table. Entire segment table in registers. Then at the time the segment table is put it in memory. Currently, what segment is referred by your CPU? Okay, that segment table base register value, limit register value kept in registers. A block of addresses stored in memory, currently referred one is stored in registers. This is segment table base register, segment table limit register. And coming to the third very important one is associative memory. Okay. So already in computer organization, you already know that what is associative memory. An associative memory is a concept where the searching of a particular word is not based on address. It is based on content or part of a content. Where searching of a particular word is not based on address, it is based on content or a part of it. In order to improve the fastness, you can use associative memory concept. Now, how protection is done? The protection is similarly like a valid and invalid bits, like paging. Now, we are also having shared pages concept, shared segmentation. Similarly, same segments can be shared by any number of processes at the same time. But your segmentation concept suffers from external fragmentation. You know what is external fragmentation? You know what is external fragmentation? The required amount of memory which is available in memory, but it is not in a continuous fashion, hence the user cannot able to run the program. And such kind of a concept is going to be called as external fragmentation. And such kind of a concept is going to be called as external fragmentation. Now, coming to the next one. Now we complete the discussion about the second kind of virtual memory concept. First, we have been seeing paging, and second one we have been seeing segmentation. Now we'll see the third kind of a concept is going to be called as segmentation with paging. The next one is segmentation with paging. Now, what is this particular segmentation with paging? It is a mixture of paging and segmentation. It is a mixture of paging and segmentation. Okay. Now we have Now, let us take an example. In segmentation, suppose we have been divided the entire program into some 5 segments. The main memory, main program is one segment. Suppose whenever the user is trying to execute a program using segmentation, first of all, main program should be copied into main memory. But if the main memory space is not sufficient for accommodating in main memory, then what you need to do? Even main program, whatever the amount of space which is required to run your main program, which is also not available in memory, then what you need to do? You need to divide the main memory into pages, main program into pages. That's why I call it as segmentation. Within that you have in paging concept. Now main program is also divided into pages. Currently which pages is required, then only such pages are going to be copied into main memory. That's why this concept is going to be called as segmentation with paging. Currently whatever the segment you are referring, if that segment is not having enough space to copy into main memory, then again that segment is divided into pages. It is called as segmentation with paging. Okay, then how we execute it? Similar manner, whenever the CPU generates a logical address which consisting of segment number as well as offset, the segment number is simply sent to the segment table. It simply determines currently whatever the segment you are referring, okay, whether that particular segment determines segment length and page table base, both are going to be determined. So whatever the length you have been written, it should be, see that your value must be always greater than or equal to your base value and less than or equal to your limit value. And after that, within that particular page, you are going to page table. Simply you are referring that whatever the page you are referring in that segment, which is going to be picked up from the corresponding page table of that segment, and it is attached to the offset in order to get the physical address. Yes. That is, simple conclusion is that we must have a separate page table for each segment. We must have a separate page table for each segment. Hence, it is going to be called as segmentation with paging. This kind of a thing is already implemented in Multics operating system. Okay, so one of the best operating system which is implement this particular concept is Multics operating system. Okay, in similar manner, we are also having multi-level segmentation where you have a segment table. We have a segment table for segments. Okay, page table for page table. Similarly, segment table for segment table. And coming to the next very important concept of this, this is completes our discussion about the virtual memory management schemes, paging, segmentation, and segmentation with paging. Now we move on to the small topics which is left over in this particular memory management. Okay, we have a small topics which is left over in the memory management is demand paging. What do you mean by demand paging? What do you mean by demand paging? The word itself, it says that demand. Okay, demand paging. Okay, and what do you mean by this? A CPU already generates a logical address. I told that CPU generates a logical address. That logical address is consisting of page number and as well as offset. The page number is going to be sent to the page table. The page number is sent to page table. The page table simply determines whatever the page currently requested, whether it is available in memory or not. In case if it is available, no problem. If the page is not available in memory, then it gives you a page fault. Whenever a page fault is encountered, what you are going to do is that you are forcibly bringing the particular page from secondary storage device to main memory. You are forcibly bringing that particular page from secondary storage device to main memory. Even though if the space is not available, by using page replacement algorithms, you are removing one of the page which is not currently required and you are bringing the currently requested page into memory. Yes, that's why this topic is headed as demand paging. Now, how can you explain this particular concept? The CPU generates a logical address that consisting of page number and as well as offset. Whatever the page currently requested, first of all, the page number is sent to the page table. The page table simply determines whatever the page you are requesting, whether it is available in memory, it is with the V available. So in case if it is available, there is no problem. It is having I, that is invalid. That is that particular page, whatever you requested is not available in memory. Then it gives you an interrupt to the operating system. It gives a system call to the operating system, whatever the page currently which is requested, which is not available in memory. Then what operating system is do is that, first of all, it checks that whether there is enough space for bringing this particular page into memory or not. First of all, it checks that whether this, as you say, there is enough space is available in memory or not. If the space is not available, then what your operating system is doing that, please try to remove the page which is not currently required in memory, and you're going to the secondary storage device, bring the particular page and copy back onto the free place. Once it has been copied, again you need to reset the page table with valid. This I should be changed as valid, and again restart your program execution. This is what is going to be called as demand page. This is going to be called as demand page. Whatever the page we are requested, it is the responsibility. Whatever the page while executing it demanded, it is the duty of operating system bringing that particular page from secondary storage device to main memory. Otherwise, the program execution is going to be simply stopped. That's why this particular one is headed with the demand paging. That is going to be headed with demand paging. Similarly, we are also having demand segmentation also. Similarly, we are also having demand segmentation. What is demand segmentation? CPU generates a logical address which consisting of segment number and as well as offset. The segment number is entered to the segment table. It simply determines whatever the current segment you are searching, what is the base and what is the length of the segment. If it is available, if it is not available, then it indicates with invalid. Then immediately it tells you the operating system that particular segment is not available. Then operating system checks that whatever the current segment which is referred, how much space is going to be required, whether that sufficient space is available in memory or not, whether sufficient hole is available or not. In case if it is available, no problem. If it is not available, remove any one of these segments and bring the requested segment from secondary storage device to main memory. And after that, again, you need to make them this invalid bit as valid and exclude. That's why it is known as demand segmentation. Similarly, like demand page. This is completes our discussion about demand page. Now coming to the last topic of discussion. So, the last topic of discussion in this memory management technique is thrashing. The last concept of discussion in memory management is going to be called as thrashing. The process is said to be in thrashing if it is spending most of the time for paging activity than execution. A process is said to be in thrashing. A process is said to be in thrashing if it is spending most of the time for paging activity than execution. Then it is going to be called as thrashing. Or you can enter as the process continues to fault, replacing the pages for which it will then fault and bring back the right way. This is thrashing. Or you may simply define as high paging activity, or you may define it as high paging activity is going to be called as thrashing. High paging activity is going to be called as thrashing. What do you mean? Now, while implementing paging scheme, what happens is that the CPU is repeatedly requesting for the pages. But whatever the pages currently are requested, if it is not available in memory, what happens? You are going back to secondary storage and bring back and copy it into main memory and you are executing it. So, while executing one page, again it causes another page fault. Repeatedly it is causing page faults. That is, if it is spending the most of the time for paging activity than execution, then we say that that process is in thrashing. That's why a process is said to be in thrashing if it is spending most of the time for paging activity than execution. Why paging is occurs? Why thrashing is occurs? If a process does not have enough pages, if the process does not have enough pages, then page fault is rate is very high. Then what is the different causes? So whenever a page, how do you reduce it? So page fault means you need to get that particular page. The page is not currently resident in memory. So you are wasting some amount of time for, and CPU cycles are unnecessarily wasting for bringing that particular pages from secondary storage device to main memory. CPU is spending some amount of time for bringing that particular pages into memory and replacing the existing frame. And you're also doing that, whatever the frames, pages which is not currently required, you're removing it and copying back. So that is swapping is done. But you already know that before swapping, you must save the status of the current process where it has been stopped. Somewhere in the saving and restoring must be done. There is a lot of time is wasted. So it implies you need to quickly replace the frame back. This leads to, by doing all these particular activities, what happens? The CPU utilization becomes very low. The main objective of an operating system is that to keep the CPU busy at all the times. The main objective of operating system is that to keep the CPU all the times. By doing this particular thrashing, by using this particular paging scheme, more number of page faults, the CPU utilization becomes very low. Then operating system thinking that it's need to be increase the degree of. Now what is the different causes of thrashing? What are the different causes of thrashing? So what you've done, in order to improve the CPU execution, in order to improve the CPU utilization, you're increasing multi-programming. So up to if there is enough space in memory, there is no problem. You can increase the number of jobs and the utilization is increased. Increase the number of jobs, CPU utilization very efficient. But up to some particular position, what happens is that in case still you are increasing multi-programming concept, in x-axis we are defining degree of multi-programming, in y-axis I have been shown CPU utilization. So up to this particular point, there is no problem. Still you are increasing. What happens is that whatever the new processes you are loading, if the new process are not having a sufficient space in memory, it uses virtual memory concept, that is paging concept. Okay, in paging concept, what happens is that whatever the page is currently you are referred, which is not available in memory, you are simply bring back from the secondary storage. Yes or no? Then you are spending a little amount of time for paging activity. And even though you are not stopped, still you are increasing the number of programs. And automatically, your CPU utilization becomes down. In some situations, it also becomes zero also. Why? Because the complete amount of time CPU is completely spending for swap in, swap out the pages from secondary storage to memory, memory to secondary storage device. That's why, so you please try to improve multi-programming, degree of multi-program up to a certain stage. Now, so that's why, what is thrashing? Continuous paging activities, or you may define it as high paging activity, or you may define it as process is busy for swapping pages in and out, or you may define it as it is spending the most of the time for paging activity than execution. Now, so finally I conclude that what is the main causes of thrashing? Increasing the degree of multi-programming. Okay, next one. In case if the page replacement algorithm is not efficient, it may causes more number of page faults, so that you are wasting so much amount of time. So these are the main causes of thrashing by increasing the multi-programming, by using poor page replacement algorithm. Now, how do you prevent this particular thrashing? How do you prevent this particular thrashing? We can prevent this particular thrashing by using the concept of working set model. But in order to practical, first of all, we'll see what is this particular working set model. Then we'll see what is that. In working set model, okay, these are the pages which is referred by the CPU at a moment of time between from T1 to T2 something. To CPU refers page to specs 1, 5, 7, 7, 7, 7, 5, so on up to like this. Now, by observing this particular string, you identify what are the most frequently referred pages. What are the which pages are morely referred by your CPU? Please try to see that pages is always resident in memory. Please try to see that pages are always resident in memory. So you please try to observe in this reference string up to T1. Okay, the most frequent pages referred by PCB is 1, 2, 5, 6, 7. So we please try to see that while up to time T1, this particular 5 pages must be currently resident in memory. And you observe the time between this to this place. The most frequently referred pages by the CPU is 3, 4. You please try to see that this particular 2 pages must be always resident in memory. So this is called as working set window of this particular reference string. This is working set reference window of time T2 of this. Okay. Okay. By observing like this, so that we can reduce the number of page faults. We can reduce the number of page faults. Now, page fault frequency. Okay, when we will see. Okay, in the x-axis we have been defined the number of frames. Okay, in y-axis we have been defined the page fault rate. Okay. If the number of frames is very less, the number of frames, or may call it as number of blocks, is very less, you may have a high degree of page fault rate. If the number of pages, if the number of blocks is increases, number of frames is increases, then your page fault rate maybe gets down. Yeah, and that implies you have enough main memory space for accommodating your pages. Then you have a lesser number of page faults. That's it. So this is completes our discussion about memory management techniques. This is completes our discussion about memory management techniques. So today what we have been seen is that virtual memory concept. Today what we have been seen is that virtual memory concept. A virtual memory is a concept which gives an illusion to the programmer that he has a large amount of memory, relatively having small amount of memory. And in order to practically implement this virtual memory concept, we have 3 kinds of techniques: paging, segmentation with paging, and after that we have been seeing the demand paging, demand segmentation, and the last but not least in the topic of memory management is thrashing. A process is said to be in thrashing if it is spending the most of the time for paging activity than execution. In order to work on this, we need to use working set model, or you need to increase the number of frames in main memory. That implies you increase the capacity of the main memory. That's it. This is completes our discussion about memory management. Now we'll move on to the next topic is going to be called as next. Now we move on to the next topic, file management. We have been left with only 2 topics. Number 1 is file management, and the last topic is secondary storage management. Maybe tomorrow is the last class for you all. Okay. Now coming to the next one, file management. Okay, we have been discussed process management, which is internally consisting of 4 subtopics: process scheduling, process synchronization, deadlocks, and we have been completed the discussion about memory management. That is memory management and virtual memory concept. Now we'll see file management. In file management, we're going to see 2 different kinds of topics. Number one, file system interface. Number two, file system implementation. What is it? Now, here, whatever the information so far we have been seeing, this all content is manipulated in main memory. So once the power is turned off, the total content of main memory is vanished. If you want to see any particular data permanently, if you want to see any particular data permanently, if you want to see any particular data permanently, it should be stored on secondary storage device. That is a hard disk or floppy drive or disk or RAM or something. But in order to store the data on secondary storage devices, we use a concept of files. A files is a programming technique which can be used to map the data onto secondary storage devices. A files is a technique which can be used to map the data onto secondary storage devices. Okay, in C language, we use the concept of files. In C language, we are using the concept of files. In C++, you're also going to be call it as files. In Java, we are going to be call it as strings. In Java, it is going to be called as strings. In any programming, any programming language, if you want to see any particular data, such can be done by using file concept. Okay, that is in this first one, file system interface. So your operating system is responsible for, suppose your operating system is responsible for doing several kinds of activities in connection with file management. Already we have been seen in the third topic discussion in file management. What are the various responsibilities of operating system in connection with file management is that your operating system is responsible for creation of files, deletion of files. Your operating system is responsible for creation of directories and deletion of directories. Your operating system is responsible for support for primitives for manipulation of operations, and your operating system is responsible for mapping the data onto secondary storage device, and your operating system is also responsible for maintaining backup. These are the various kinds of responsibilities of an operating system in connection with file management. Now, so this particular file management topic, we are going to be dealing in two dimensions. Number one is file system interface, how your operating system is providing a file system interface so that the user can conveniently store the data onto secondary storage device. Okay, and second very important one is that how it is implemented practically, how it is going to be implemented practically, that is file system implementation. Okay, this is what is going to be called. These are the two topics what we are going to be learning in operating system file management. Now, before going to the detailed discussion about file definition, before going to the detailed discussion about files discussion, these all files are going to be kept on your secondary storage device. These all files are going to be kept on second. With this classroom okay, first of all, we look into the hardware structure of file system. The hardware structure of file system. Okay, so how your hard disk is going to be used? Now we'll see the physical structure of hard disk. You observe in the top diagram. You observe in the top diagram. Your hard disk. First of all, this is a physical representation of your hard disk. This is your physical representation of your hard disk. This is your physical representation of your hard disk. Your hard disk is having a collection of platters. These are going to be called as platters. These are going to be called as platters. Okay. The hard disk is a collection of platters. These all platters are connected through a spindle. All platters are connected through a spindle. Spindle in the sense simply a rod. You can simply a small rod. Now, each and every platter is having two surfaces. This is upper surface and having lower surface. Each platter is having upper surface and as well as lower surface. And each and every surface is connected with one read-write head. This is read-write head and this is another. This is called it as arm. This is arm and this is read-write head. Now these all read-write heads are connected to boom. This is going to be called as boom, or we call it as arm assembly. This is called as boom. Now this heads will not going to be rotated at all. These heads all are fixed. Only the disk will going to be rotated. Only the disk will going to be rotated. So your hard disk is a collection of platters. Each and every platter is connected to a read-write head. Okay, these platters are going to be rotated. The head will not going to be rotated. Each and every platter is internally divided into number of tracks. This is one track. This is another track. This is another track, like this. Each and every platter is divided into number of tracks. Each track is furtherly divided into number of sectors. Each one is going to be divided into number of sectors. What is a sector? A sector is the smallest representable unit on a secondary storage device. A sector is the smallest representable unit on, this is one sector. It is the smallest representable unit on a secondary storage device. A sector is the smallest representative segment. It is of maximum size of 512 bytes. It is of 512 bytes. So now you can do the problems on this. One sector, collection of sectors is equal to one track. Collection of tracks is equal to one platter. Collection of platters is equal to your hard disk. So hard disk capacity is simply defined as it is a collection of platter. A platter is a collection of tracks. A track is a collection of sectors. A sector is the smallest representable unit on a secondary storage device. A sector is the smallest representable unit on a secondary storage device. Okay. Now, this is now if you view this particular hard disk from the top, you have the circles like this. The circles are going to be called as cylinders. The circles are going to be called as cylinders. That's why we are also defined as your hard disk is a collection of cylinders. Your hard disk is a collection of cylinders. This is a physical structure of a hard disk. This is a physical structure of a hard disk. So why hard disk is very popular today, apart from remaining all the secondary storage devices, because of two reasons. Number one, your hard disk is a random access nature. Your hard disk is a random access nature. You can access anywhere on the hard disk at the same time. Whereas in the case of a tape browse, if you want to go for fourth track, first you need to read first track, second track, third track, then you need to go for fourth track. But whereas in the case of hard disk, you can directly move on to any track or any sector at the same time. It is a random access device. And second very important point is that this disk allows you simultaneous peripherals operation online. Already we have been seeing this particular topic in third topic in first chapter in introductory. Simultaneous peripherals. And your disk allows you multiple operations at the same time. Your disk allows you multiple operations at the same time. Your disk allows you to do multiple operations at the same time. You can read the information from this platter, and you can write information on this platter. You can read information from the platter simultaneously. And more than one job can be done simultaneously on the hard disk at the same time. That's why hard disk is defined as pooling. What is pooling? Simultaneous peripherals operation online. Simultaneous peripherals operation online. This is what is going to be called as the physical structure of the hard disk. This is a physical structure of the hard disk. Now we are going to be come back to logical structure of the hard disk. Now we're going to see logical structure of the hard disk. The logical structure of the hard disk is divided into number of partitions. Each and every partition is a collection of directories, and each and every directory is a collection of files. We'll see what is file and what is the rest things. We'll see tomorrow. There's no problem. Just we'll define why, because these all files are going to be kept on secondary storage. Your hard disk is divided into number of partitions: E partition, E partition, E partition, like this. Each and every partition you have a number of directories inside of it. Yes or no? Bhavya, Nikita, Hari, something directories. Each and every Bhavya directory internally contains the list of all files which is corresponding to Bhavya. That's it. This is a logical view of your secondary storage device. So we haven't seen the physical view of secondary storage device, that is hard disk. This is a logical view of secondary storage device. This entire things are going to be done by your operating system. So now, in order to keep the data on your secondary storage devices, we use that concept of files. Whenever the user want to place any particular data permanently on the secondary storage devices, then we use the concept of file system technology. So what is this particular file system technology? What are the different kinds of file management techniques? Such kind of techniques we're going to be deal you in the next session. Okay, we're going to be seeing in the next session. This is what we have. So from the conclusion of today's is that, so we want to see file management, and we have been left over with only two topics: file management and secondary storage management. In file management, we see two topics: file system interface and file system implementation, and secondary storage management. And in file system interface, today what will happen is that what is the physical structure of hard disk and what is the logical structure of hard disk. The physical structure of hard disk is, it is a collection of platters. Each platter is a collection of tracks. Each track is a collection of sectors. This is and a logical view of your secondary storage device, that is hard disk is, your hard disk is a collection of partitions. Each partition is a collection of directories, and each directory is a collection of files. This is what is the concept. So we'll see the rest of the things tomorrow. This is ends of today's presentation. We'll see the rest of the tomorrow. Okay, maybe the tomorrow is the last class. I hope. I'll try my level best. Yeah. Can I stop presenting? Yeah, it is done. Okay, maybe tomorrow is the last class. I hope I'll try to finish by tomorrow. Okay. Thank you. Can I leave?